I want to talk about the cost of 3D NAND memory measured as dollars per gigabit and what levers do I have to essentially reduce this cost and bring this cost down. So I want to start from this very first 3D NAND memory, which was detailed by Samsung in this ISCC paper. And this memory, it had a capacity per die of 128 gigabit in a die which was the size of 133 square, and it was made using 24 layers of word lines, and each cell was storing 2 bits. So if I estimate how many holes would I have to make, how many channels holes to essentially enable this memory capacity. So to do that, I essentially say, okay, I have 128 gigabit of cells, or essentially 128 into 2 to the power of 30 bits, and each of these channel holes essentially has 24 cells. It comes from here, so I divide this by 24, and then each of the cell additionally stores 2 bits. Okay, so that this gives me the number of holes or number of channels I need to make to essentially enable this memory, and the number turns out to be approximately 2.5 billion cells, or sorry, 2.5 billion channel holes that I would need to make to essentially enable this amount of memory capacity. So 2.5 billion means approximately 50,000 holes in this direction, and also 50,000 holes in this direction. So that would give me a total of 2.5 billion holes in each of this die. And keep in mind, this is almost the size of your fingertip, and think of it like you're making 2.5 billion holes in your fingertip. So now to reduce the cost of this chip, I have two variables to play with, okay? So one thing I can do is increase the memory capacity in the same die size. So I can do that by increasing the number of word lines I have in each of these holes, so I can increase the word lines number of layers that I have from 24 to 32 to even 48 and so on. I can also have some headroom here to also increase the number of bits per cell from 2 bits per cell to 3 bits per cell, and that would essentially increase the numerator in this equation. I can also essentially reduce my cost by decreasing the denominator in this equation, that is packing these channel holes more closely with each other, such that I can pack the same amount of memory, maybe by using just a smaller die, maybe just using 100 square, and hence I can produce more dies per wafer, and again that would lead to reduction of the cost. So in this video, let's talk about this denominator, that is, how can I pack these holes more closely with each other. So the first thing that you probably already guessed is that you would pack these holes in a hexagonal configuration or a HCP packing to essentially achieve the maximum density that you can. Okay, so shown here is that same first generation of product from Samsung, and it has 24 of these 24 of these cells in each of these holes. As I said, one way to essentially decrease the cost is increase this from 24 to 32 to 48, and also store, instead of storing just 2 bits per cell, you can store 3 bits per cell. Okay, but to optimize, and even if you do that, you would still want to pack these cells as efficiently as possible. And to do that, you essentially pack these channel holes in a hexagonal configuration shown over here. So these cells, as you can see, they are packed in this honeycomb or these HCP packing. If you're familiar with how atoms are packed, this is the HCP packing, or these hexagonal packing as shown over here. And in each of these dies, as I talked about, you have 2.5 billion of these holes on the size of your fingertip, and that leads to 50,000 holes in your lateral direction, and also 50,000 holes in this both x and y direction. So now let's look at the commercial product, which is based on the second generation of this same VNAND architecture from Samsung. So one of the things that we have discussed in some of the previous videos, and I recommend if you haven't watched them already, go watch the videos on the gate replacement flow of VNAND that you can locate on the same YouTube channel. And they essentially talk about the process flow for making this NAND flash memory. And what it involves is essentially it involves these slit lines that you have to make this gate replacement. So you start with oxy ON layer of stack, and then you replace this nitride with the tungsten metal gate. And to do that, you need to make these slits which essentially split your word line. So here's the second generation of this memory. It has 32 of these word lines, and then you have these slits which are essentially splitting your word line into these multiple strips. And in this figure you can see very clearly that along each of these strips you have 4 lines of these cells. Okay, so you have 4 lines of these cells, as you can see over here, and perpendicular to this would be your bit line. So this is my word line, and perpendicular to this would be my bit line. Okay, so now by doing this hexagonal packing, what I've been able to achieve is I've been able to achieve 4 lines of these cells of these channel holes, which are stacked into each of these word line strips. And this allows you to make a wider word line strip, which lowers the resistance in each of these word lines. Also, you can see that I've been able to pack these things very efficiently, and the diameters of each of these cells, it can be somewhere around 120 nanometer, and the pitch between these individual cells can again also be around 160 nanometer. But I can still keep the pitch, which is the distance between each of these channel holes looking along the bit line direction, to be just 80 nanometer. That is half of this pitch between the individual holes. So I've taken this picture from this website, and also some other reports from Chipworks and so on. They report that the pitch between these slits is roughly around 750 nanometer, and the pitch between these contact holes is around 80 nanometer. So even though I have a much wider diameter of the each contact hole, by packing them in this hexagonal manner, I can enable this smaller pitch between my contact holes looking along the bit line. So shown here is this final picture from the top, and you can see it reports the same number. The distance between these two slits, which divide my word line, is approximately 750 nanometer. But and also the distance between these channel holes is 160 nanometer. But I'm able to keep the channel hole pitch, this channel hole pitch, to be equal to 80 nanometer by using this hexagonal packing of my channel holes. Now another interesting process technology that is used to further essentially give you even higher density and minimize your array overhead is that you use these bit lines which are very closely spaced to each other, okay, and they connect to these channel holes using this twisted metal one lines, okay. So these bit lines, they are in the metal 2 layer, okay, and they are connecting to these channel holes using a metal 1 layer which is twisted. So you can see that this channel hole is connected to this bit line, and the channel hole which is next to it is connected to this other bit line, and the bit line pitch is actually very small. It's a very small pitch of 20 nanometer between these bit lines, uh, and this allows you to essentially again reduce your area overhead of the array, because now you can have these longer bit lines, and where they need to drop, that's where they will add area overhead. You can minimize that by essentially having these dense bit lines, and they are alternatively connecting to these channel holes. So you can see that again similar pattern repeating here. This particular bit line is connecting to this channel hole, while this channel hole which is next to it vertically is connected to the next bit line.